Hey guys, alright, so today we're going to do the first electricity and magnetism free response that I've uploaded up here, okay? Alright, so it's going to be 1991, and it's the first open-ended, okay? So, a sphere of radius r is surrounded by a concentric spherical shell of inner radius 2r and outer radius 3r, as shown above. The inner sphere is an insulator containing a net charge of plus Q distributed uniformly throughout its volume. The spherical shell is a conductor containing a net charge of plus Q, different from plus Q. I'm sorry, I didn't read that right, but it's small q and bigger Q. Alright? So, that's the picture. And I drew in, since this is a positive Q, this gotta be the negative Q out here, and then the positive Q's accumulate here, okay? Alright, so they want you to use Gauss's law to determine the electric field for the volume values of R, the distance from the center of the insulator. Alright, so for A, they want 0 is less than little r, which is less than big R. So basically, they want the radius to be somewhere inside the sphere, okay? So let's start with Gauss's law, which means flux is going to be equal to the closed surface integral of the electric field times the surface area, which is also going to be equal to the enclosed charge over the permittivity constant. That's Gauss's law, right? So we're not talking about flux, so we'll just be using this part. So the electric field is going to remain constant, so we can take that out. So we get the electricity field times the closed surface integral of the surface value is going to be equal to the enclosed charge times the permittivity constant. Alright, so right now we are going to try and find just the enclosed charge. Because we're not getting the entire circle, we're going to put a Gaussian sphere inside of this actual little circle. We're not going to have all of the enclosed charge, so we're going to have a fraction of the final. So in order to find that fraction, we do the volume of the smaller one, which is going to be 4/3 pi r cubed, which is the volume of the sphere, times the charge that they give us, over the total volume of the sphere, which is 4/3 pi big R cubed. So when you do it out that way, the 4/3, I'm sorry, I'm doing this backwards, so it's not really accurate, but both the 4/3 and the pi's cancel. So we're going to get the enclosed charge is equal to little r cubed times Q over big R cubed. And there we go. That's the Q enclosed. So basically, now we're going to take this and plug that in for up here. Okay. The surface area of a sphere is going to be equal to 4 pi r squared. So we're going to plug that in too. So you're going to have the electric field times 4 pi r squared is going to be equal to r cubed Q over r cubed times the permittivity constant. Basically, that's what we have. And we want to solve for the electric field. So we're going to divide both sides by the surface area. Okay. So basically, you're going to end up getting, because the little r's are going to end up canceling. So you're going to end up with Q times little r over 4 pi permittivity constant times big R cubed. And that's what you get. But if you want to condense this, 1 over 4 pi epsilon right here is going to be equal to K. So you're going to set that equal to K times Q times little r over big R squared. And that, my friends, is the electric field for little r is between 0 and big R. Okay? Alright, so now for B, they want us to find the electric field for when little r is between big R and 2 big R. So basically, in this empty space right here, they want to find what the electric field there is. So again, we go straight to Gauss's law. But this time, the Q enclosed is just going to be equal to the charge of the entire insulator sphere right here. So basically, we don't have to do the whole fraction thing to find out what amount of the charge is enclosed. So let's take it from the second step of Gauss's law. So you can have E, which is the electric field, times, again, we know the surface area, so it's going to be 4 pi r squared is going to be equal to big Q because that's the enclosed charge. And that's going to be, again, over the permittivity constant. Where are you? All right. So this is what you have. Again, divide both sides by the surface area. And substitute K in for 1 over 4 pi times the permittivity constant. And you're going to get E is going to be equal to KQ over R squared. And that is the electric field for the space surrounding the insulator, okay? Right here, in between the insulator and the conductor. But now for C, they want us to find the electric field such that little r, which is the radius or the distance from the center, is between 2r and 3r. So basically in the conductor range. Sorry, right there. In this little ring is where they want you to find the electric field. But what do we know about conductors? Inside of a good conductor, the electric field is 0 by definition. So we don't exactly have to do any work here as long as you state, you know, by definition, a good conductor means that there's no electric field inside, and therefore E is equal to 0. And so there's C. Now let's see D. They say determine the surface charge density, which is the charge per unit area, on D, the inside surface of the conducting shell. All right. Okay, sigma is the symbol for surface charge density, and they give it to you. They say it's going to be the charge per unit area. Charge per unit area. There you go. Okay, they want the inside surface of the conducting shell, and that is going to be equal to this. This is what this is. And because you know that the inside is positive, this area must have the negative. That's going to be the inside of this. So it's going to be equal to negative Q over, and then the surface area, which is going to be equal to 4 pi, is going to be r squared. But this is actually equal to 2r, so you have to submit 2 times big R squared. So you're going to have 2 times big R squared. So basically, when you do that out, you're going to get negative Q over 16 pi big R squared. And that is the surface charge density on the inside of the conducting shell. Now, for the last part of this question, which is E, they want us to find the outside surface for the conducting shell and the surface charge density there. So we do the same thing again. It's going to be sigma, again, it's going to be equal to the Q over A, but this time, outside, we're going to have the charge given and then the charge caused because this is negative. So the total charge on the outside is going to be little q plus big Q. So it's going to be little q plus big Q, and again, it's going to be 4 pi, but now this time, the outside is a radius of 3r, so that's where the 3r squared is. So you're going to do 3r squared, and from that, you're going to get q plus q is equal to 36 pi r squared. And that is the surface charge density at the outside surface of our conducting shell. And therefore, we are done with this problem. So I don't think it was so bad for my first electricity and magnetism problem to be posted up here. And I hope you guys found it somewhat helpful because I'm still new and getting used to this. If you have any questions, suggestions, comments, please let me know. Thanks for watching and have a great night. Bye-bye.